We don't have a lot of people here, so I want to wait a minute or two and just see if we get some more people. I wonder if internet issues are making it hard or something. Who knows? Yeah, let's just wait another minute or two and just see. So I'm just waiting another minute or two to see if we get more people. About half of the classes here, maybe a little less. Just waiting a minute or two and seeing if we get more people. Pretty cat, Kevin. It's a beautiful cat.
Thanks. Her name is Perdita.
We'll say it one more time.
Perdita?
Perdita, that's pretty.
We call her Purdy for short.
She's got blue eyes, very pretty. All right, I think let's get started and we'll just see if more people show up. Now I'm getting more people. Let's see. Okay. Okay. All right. So I want to finish the endocrine system here. Bear with me. Where was I? Endocrine system. Okay. So one more shout out, and I got, and Isabel, I think I do remember you sending me your home address before.
Okay, I just want to double check.
Yeah, when I went to look for it again to write them down, I couldn't find it.
Okay, that's okay.
So one more shout out about that. Send me your mailing addresses if you want to participate in the urinalysis lab next week. A lot of this stuff I just show you, or I do the dissections, and you don't ever get to perform anything. I wouldn't mind if you got to be involved next week. I'd like you to be involved, which means that I need to send you something in the mail. And so send me your home addresses if you want to be involved. And I'll explain by here in a moment just what else will be required for that. Let's finish the endocrine system PowerPoint here.
Ms. Mary,
Yeah,
before we get started, shortly, I'm gonna have to switch from my laptop to my phone. So I don't know, my internet's a little shaky right now.
okay.
So if you see me disappear and come back, that's why.
Okay, I still want to talk to you
Yeah.
some point today after
Okay.
class, or tomorrow, or whenever is easiest for you.
Okay, sounds good.
Oh, why am I doing this? Bear with me, guys. So last part of this are hormones that come from tissues that technically are not really considered organs of the endocrine system. However, they are hormones. The stomach and the small intestines secrete five different types of hormones, 4 specific ones and other enteric hormones. Cholecystokinin, gastrin, ghrelin, I think that's how it said, ghrelin, peptide Y, and other enteric hormones. Cholecystokinin is involved in bile release and appetite suppression. Gastrin's involved in stimulating stomach acid secretion. Ghrelin is involved in stimulating hunger and initiating feeding. Peptide Y produces a sense of satiety, as I can't say the word. Satiety, what is this word?
Satiation.
That's kind of, yeah, doesn't end that way, but satiety or satiation, and terminating feeding. Other ones work to secrete motility in different regions of the digestive tract. We will talk about some of these when we talk about digestion and where they're specifically their functions then. Adipose tissue secretes leptin, which over time limits appetite. Osseous tissue secretes osteocalcin and lipocalin, both of which are involved in insulin secretion. Atrial natriuretic peptide is involved in regulating blood pressure. Atrial natriuretic meaning it's coming from the right atrium in response to increased stretch of the right atrium. So when the heart is pumping with blood, we get it when there's too much, atrial natriuretic peptide is secreted. And the result is that it causes vasodilation, dropping blood pressure. If you've Remember, if you dilate the blood vessels, you drop the blood pressure. It also is involved in dropping renin. Remember, renin is involved in increasing blood pressure. And renin is going to work on angiotensin 2, and angiotensin 2 is going to work on aldosterone. Remember that aldosterone from our actually, the original aldosterone is involved in bringing up water volume in the blood. And all with atrial natriuretic peptide and decreasing renin is going to result in decreasing blood pressure and decreasing blood volume. Because if you decrease blood volume, you decrease blood pressure. So hormones that originate from the liver, kidneys, and heart. The skin cholecalciferol, if you remember this one from before, it's one of the precursors in producing vitamin D. Liver calcidiol, also one of the precursors of producing vitamin D. Remember, calcitriol is the active form of vitamin D. Liver also secretes angiotensinogen, which is the precursor for producing angiotensin 2, which is what renin acts on. Let's see here. Erythropoietin, remember that's involved in producing red blood cell production. Hepcidin targets the small intestines and liver, regulating plasma iron levels. Insulin-like growth factor prolongs the and mediates action of growth hormone. So insulin-like growth factor and growth factor work in conjunction with one another, and they're synergistic of one another. Kidneys, angiotensin 1, precursor of angiotensin 2. Calcitriol, remember this is like vitamin D, the active form of vitamin D. Works on the small intestines to increase blood calcium absorption. Erythropoietin in the kidneys. So if you look here, we didn't study this before, but the liver is going to produce erythropoietin, and so is the kidneys. Both of them are going to do it. And the heart, natriuretic peptides, kidneys, working on the kidneys to reduce blood volume. One last thing. Eicosanoids. We talked about this when we talked about the nervous system and neurotransmitters, that these are a neurotransmitter in many ways. Remember, a lot of our hormones are neurotransmitters. A lot of our neurotransmitters are hormones. Just depends on where they're acting and what receptors they're binding to. Eicosanoids are paracrine signals, meaning they're being released from some cells just to affect neighboring cells within the same tissue, rather than being secreted into the bloodstream and circulating throughout the body and going somewhere. These, on the other hand, are being sent to a specific tissue. Sorry, they're being isolated within that tissue. So these are chemical signals that are not going to travel in the blood, but they're going to exert their effects locally. These all eicosanoids are coming from the precursor of arachidonic acid. arachidonic acid formation is blocked by cortisol. Talked about how different hormones regulate other hormones. Cortisol is going to block the development of arachidonic acid, meaning you're going to slow down eicosanoid production. Lipoxygenase takes arachidonic acid, an enzyme, lipoxygenase, producing leukotrienes. If you listen to that name alone, it has to do with leukocytes that are involved in the immune system. Cyclooxygenase, which you may not be familiar with, but you're familiar with its effects because this is what Tylenol and ibuprofen work against. Cyclooxygenase is going to take arachidonic acid and convert it to prostacyclins, thromboxanes, and prostaglandins. This is the enzyme that's inhibited by aspirin and ibuprofen. Some of the roles of different prostaglandins being produced by cyclooxygenase. We have inflammatory prostaglandins, promote fever and pain, two of the main cardinal signs of inflammation. They're endocrine, they mimic the effects of thyroid stimulating hormone and adrenocorticotropin hormone and other hormones, altering the sensitivity of the anterior pituitary to hypothalamic hormones. So altering that interaction between the hypothalamus and the anterior pituitary. It also works with glucagon, catecholamines, remember they're coming from the adrenal medulla, and other hormones in regulating fat mobilization. The nervous system function as neuromodulators. Zena probably remembers this best because we just talked about it in 121. Altering the effects of neurotransmitters in the brain. Reproductive, promoting ovulation and formation of the corpus luteum. So these would be involved in the luteinizing hormone production and allowing it to form the corpus luteum. Inducing labor contractions, so working with oxytocin. Gastrointestinal, secreting gastric secretion. Inhibiting gastric secretion. Vascular, acting as a vasodilator and vasoconstrictors. Working in the respiratory system to constrict or dilate bronchioles. So these are all paracrines produced by cells within the same tissue to work on nearby cells within that same tissue. Renal, promoting blood circulation through the kidney, increasing water and electrolyte excretion. The last part. True or false? Hormones are normally secreted via ducts into the bloodstream.
False.
False, because it's not, they're ductless, like Kevin said. Many effects of growth hormone are mediated by insulin-like growth factors secreted by the pancreas.
Is it false?
Why is it false, Rachel?
Because Aren't they secreted by the liver?
Good job. Yes. Cholesterol is essential for the synthesis of steroid hormones.
True.
True. Regardless of the cause of stress, the body reacts in a fairly consistent way to different stressors.
I want to say true.
It is true. So it doesn't matter if it's stress over an exam, stress over an economic issue, stress over a child doing something that is making you frustrated, or stress over the fact that you've been physically injured. Your body always acts in the same way. Prostaglandins are considered paracrines.
True.
True. Okay. You guys, that is the end for the endocrine system. Are there any questions? So like I said before, use for the, especially for this chapter, use flashcards because there's a lot of information here and a lot of it is memorization. All right, let's jump into something else. Let's look at the kidneys and what I plan on, if we have time today, after the dissection, I want to look at a little bit of respiratory because that's what we'll get into lecture next week. We are running a little behind schedule, and what I may do is we had 2 weeks to do the reproductive system. I think I can do it in a week, just leaving certain things out. And so I think that's what I'll do. But let's just see how things continue to go forward. The kidneys are something that we normally take for granted until they don't work. We don't, you can get down to where you have 3% kidney function before you recognize that your kidneys are failing. So looking here, you'll see this PowerPoint is not very long. It's going to be a fairly short PowerPoint. There's a lot of information about the kidneys. They're more complicated than we like to think they are. But we'll cover this lab this week is going to cover the urinary system. Next week's lab is going to cover urinary system. So we'll cover it in 2 different labs. So the urinary system, the different organs include the kidneys, the ureter, the bladder, and the urethra. Your, so bear with me, your right kidney sits a little lower than your left kidney does, based on the fact that your liver is right here. Transverse section looking at the kidneys shows that they are behind, they're behind the liver. Here's the right, excuse me, right kidney, here's the left kidney. Here's the pancreas. Here's the spine. So here's the anterior surface, posterior surface. The liver, part of the small intestines, the stomach, the pancreas sitting behind the stomach, the aorta, the descending aorta or abdominal aorta, and the inferior vena cava. The spleen being over here. This whole area, starting from about right here and all throughout right here, is considered the peritoneal cavity. Peritoneal cavity. So peritoneum is the barrier, this barrier right here. This barrier right here. That's the peritoneum. All of this cavity right here is the peritoneal cavity. What that means is that the kidneys are considered retroperitoneal, meaning they're behind the peritoneum. This is important anatomically for a lot of different reasons. But right now, just know that that's why we refer to the kidneys as being retroperitoneal. Any questions so far? Looking at a cross section through the kidney to look at the major anatomical structures. Right, we have right at the very outer edge, we have a renal cortex. We've seen cortex before. For example, the cerebral cortex, the cortical bone. I think we see it, there's a cortex in the lymph nodes. There's a cortex in the medulla. Excuse me, not cortex in the medulla. Medulla in the lymph nodes. So here we have a renal cortex, renal meaning kidneys, renal cortex, renal medulla. The outer layer is the renal capsule. Surrounding the renal capsule is a renal fascia, which is an extension of the peritoneum. And just deep to the renal fascia is an adipose capsule that also is going to surround the kidneys, protecting them. When looking at a cross section through the kidneys, and you'll see when we're looking at a dissection, it looks very similar. Kidneys are probably the easiest when it comes to dissection and identifying things because it looks so similar. So the renal cortex surrounds the outside and then it extends in, forming the renal columns that separate renal pyramids that look like triangles. At the tip of each of the pyramids, there's a renal papilla. Papilla meaning a nipple. So a renal papilla, a little nipple. The urine is going to flow down this little thing right here called the collecting duct, which is part of a nephron, which we'll talk about next. It's going to flow down this collecting duct and leak into the renal papilla, which is going to drain into what's called the minor calyx. The minor calyces are going to merge together to form a major calyx. The major calyx is they're going to merge together to form the renal pelvis, which is in the renal sinus. And so if we're looking at this, the urine is going to leave the collecting duct. Once it's formed, it's going to leave the collecting duct. It's going to drain in the renal papilla. It's going to flow into the minor calyx. And the minor calyces are going to merge together to form major calyces. And the major calyces are going to merge together to form the renal pelvis, which is going to, and from there, the urine is going to flow out into the renal hilum, which is going to form the ureter. This right here would be the ureter down here. The blood flow coming into the kidneys, because that's another thing that we're going to consider, is that there is a lot of blood flowing through the kidneys. I'm trying to remember. I think it's 625 ml of blood per minute flows through the kidneys. And if you consider that you have about 5 liters of blood, that means that at least every 10 minutes, all of your blood is going to flow through your kidneys. So the renal artery is going to supply the blood to the kidneys, and the renal vein is going to drain it. This is just another comparison slides looking at a fixed kidney versus the diagram. The renal cortex, renal columns, the renal pyramids, the minor calyces, which merge to form major calyces. Major calyces become renal columns. Actually, I'm sorry, major calyces, I thought that doesn't sound right. Major calyces merge to form the renal sinus, into the renal pelvis, into the renal sinus. Excuse me, let me start that again. Minor calyces merge to form major calyces. Major calyces are going to merge to drain into the renal pelvis. The renal pelvis is located in the renal sinus. As the renal pelvis extends out of the kidney via what's called the renal hilum right here, the renal pelvis is going to become the ureter. Are there any questions? So actually the most important part, so this was talking about just the gross overall anatomy of the kidney. Shifting gears, the nephron, if you think nephrology is a study of the kidneys, the nephron is the functional unit of the kidney. It includes a glomerulus, which looks like, glomerulus means like a ball of yarn, ball of string. Like, and so I like to think of this as it's a knot of capillaries. And so the glomerulus is this knot of capillaries where an afferent arteriole is bringing in blood and an efferent arteriole is draining this glomerulus. Surrounding this glomerulus is a glomerular capsule, or we also call this Bowman's capsule, BOWMAN', Bowman's capsule. But the glomerular capsule is going to lead into the proximal convoluted tubule. The proximal convoluted tubule, if you think what it means to be convoluted, meaning it's all over the place, it's very twisty and complicated. That's the proximal convoluted tubule. Proximal because it's right next to the glomerulus. Convoluted because it's all curvy and twisted. We have this descending loop of Henle, this big loop, descending loop of Henle, and then an ascending loop of Henle. An afferent arteriole. Oh, why did I say afferent? Excuse me. Ascending limb of Henle, distal convoluted tubule. And one thing that I want you to take note of here is that the glomerulus and the distal convoluted tubule and the afferent arteriole are right up against one another here. This is going to be important later. They're like right next to one another. So the distal convoluted tubule is going to drain into the collecting duct. And remember that the collecting duct is going to drain into the renal papilla via a renal papillary duct. Now, one thing with regards to kidney function, a really good way to start learning how this all works, because I think that kidney function is probably one of the more complicated things to learn about. I'm going to stop sharing for 1 second, and I'm going to make my best effort to draw you this nephron. And you know what the drawings look like. So we're looking at kindergarten-like drawings, but we're going to try. So let's see. Here's my glomerular capsule. And let me tell you, if you start learning how to draw this, draw it out, you will understand it more than if you don't draw it out. But I'm going to put this, here's my proximal convoluted tubule. And then it moves into the descending loop of Henle. then the ascending loop of Henle. Now, so that I don't mess myself up here, I'm going to draw my, finish drawing this. Hopefully I'll do a reasonably good job. Something like this. Okay. So like that. And then the ascending loop of Henle, this loop that's coming up here, is going to move into my distal convoluted tubule. And before I draw that, I'm going to change colors. And I'm going to draw my arterioles. My afferent arteriole coming in like this. And my efferent arteriole coming out like this. So blood is coming in this way. And it's leaving this way. Remember what afferent means. Afferent always means incoming. So it's the blood that's coming into this glomerulus. The efferent arteriole is where the blood is leaving. So then I have this big knot. And that's a terrible drawing. I told you it looks like a kindergartner. But here it is right here. This is my knot of my glomerulus. So then, also, I have to finish drawing my nephron. So I'm going to draw this so that it comes up behind here. And it's right here. It's going to be my distal convoluted tubule. It's distal because on the whole scheme of the nephron, it's farther away when I have to go all the way down like this and come up here to be that close to the glomerulus. It's in the loop of the nephron. It is much further away. That's why it's the distal convoluted. So we're going to draw it. So it's just like this. And then this is going to be my collecting duct. So that's my drawing of my nephron. Now, shifting backwards again. That's the same drawing, but using my kindergarten writing with the whiteboard. So most of my loop of Henle, if you look at how it's located, most of the nephron, the distal convoluted tubules, the proximal convoluted tubules, and the glomerulus are all located within the cortex of the kidneys. With the loop descending into the medulla. There's two different types of loops. One of them is going to descend significantly into the medulla. One is not. And we'll talk about those later. But for right now, know that most of outside of the loop, all the nephron is going to reside in the calyx, assuming in the cortex. Now, another thing to include here in our big old drawing is looking at the blood circulation, because like I said before, there's a lot of blood circulating around the kidneys. So that we have this afferent arteriole bringing in blood, the efferent into the glomerulus, the efferent arteriole taking it out. The efferent arteriole is going to bisect into two different types of capillaries. It's going to separate into two branches of capillaries. It's going to branch off into the peritubular capillaries. Remember what peri means. Peri means surrounding. Tubular meaning around tubes. So the peritubular capillaries are going to surround the proximal convoluted tubule and the distal convoluted tubule. The vasa recta, on the other hand, which is also going to divide off from the efferent arteriole, is going to surround itself around the loop of Henle. So afferent arteriole moves into the glomerulus, efferent arteriole leaves. Efferent arteriole is going to divide off into peritubular capillaries and the vasa recta. Excuse me, bear with me. The peritubular capillaries and the vasa recta will then merge together again to form what's called the interlobular vein. So adding this to my drawing before, here's my efferent arteriole, here's my afferent arteriole. My peritubular capillaries are going to come and they're going to surround the proximal convoluted tubules and the distal convoluted tubules. In addition to them surrounding the distal and proximal convoluted tubules, the recta is also going to be a branch off the efferent arteriole, and it's going to come down and it's going to surround the loop of Henle. And one thing that's really important here that we'll see again later is that even though the filtrate is moving this way, moving from the capsule into the proximal convoluted tubule and down the loop of Henle, then up the to the distal convoluted tubule, the vasa recta, on the other hand, even though the filtrate that's coming out of the glomerulus, even though it's flowing this way and flowing back down and around, the blood, on the other hand, of the vasa recta is coming down the opposite direction and going right to left. Keep that in mind. It will help you significantly later. So the fluid in the nephron is going from left to right here. In contrast, the blood that's surrounding the loops, or at least the vasa recta, is flowing right to left. Now I don't see any faces for right now. Thank you. So spanning out a little bit here, we're looking at the histology. Remember that most of the nephron, this is showing the histology of the kidney cortex. Most of the nephron, the proximal and distal convoluted tubules, is in the cortex. So the glomerulus, the proximal and distal convoluted tubules, and a lot of the loops of Henle are going to be found in the cortex. Let's scan in just a little bit. Looking at the glomerulus, oh, it doesn't show you this, but this right here, here's the glomerulus, here's the glomerular capsule or Bowman's capsule, and there's a space in here. Surrounding the glomerulus, here's some of the proximal convoluted tubule. The distal convoluted tubule would be about right here, right next to that afferent arteriole. So looking a little bit more at the glomerulus, it looks like a ball of string. That's where the name comes from. It's got a bunch of podocytes. Remember what means? Podocytes means foot processes. So it's got a bunch of podocytes affecting filtration slits. Now, if I say filtration slits, what that means is that this is where we're going to get a lot of filtration of blood plasma. Do you remember from a couple weeks ago talking about those different startling forces that are involved in capillary blood exchange? How we had a hydrostatic pressure and a colloid osmotic pressure and so forth. Hopefully you do. If you don't, review some of that, because that's what's occurring here also. That's going to result in the filtration of the blood plasma within the kidneys. So we have this knot of strings that are going to be involved in regulating filtration slits, allowing plasma to be filtered here in the glomerulus. Things that can't move through these slits won't be filtered out into the nephron. Other things will be filtered out. And I'm gonna, you know what, I'm gonna shift or no, I'm gonna leave it the way it is for right now. Another thing, bring up here, is blood supply to and from the kidney and the nephron. So we talked about how the afferent arterial is supplying blood to the glomerulus. The efferent arterial is draining the blood from the glomerulus. Paratubular capillaries around the proximal and distal convoluted tubules, and a vasa recta around the loop of Henle. How does the blood get to the afferent arterial? The blood gets to the afferent arterial via the renal artery. So the renal artery is supplying the blood to the kidneys. It's going to branch off into the segmental arteries. And the segmental arteries are going to go up in between the pyramids. One thing that we didn't mention before is that each area, this little area right here, this area right here, this area right here, this area right here, this area right here. These are called lobules. L-O, oh, actually, let me. These are called lobules. So when we're looking at the kidney, like so, here's our pyramids, as I can't draw. Here's our pyramids. Here's our pyramids. And so forth. This area right here is a lobule. And the reason I say that, and the reason I bring it up, is because these arteries, once the segmental arteries branch off, they become interlobar arteries, meaning they're going in between the lobules. So renal arteries become segmental arteries. Segmental arteries are going to move up in between the lobules, forming the interlobar arteries. The interlobar arteries move up and arc over the pyramids, forming the arcuate arteries. The arcuate arteries are going to become the interlobular arteries. And the interlobular arteries are going to branch off into the afferent arterioles. The afferent arterioles go into the glomerulus, circulate around, come back out, and the blood drains into the efferent arterioles, which, remember, the efferent arterioles are going to branch off into the paratubular capillaries and the vasa recta. they will merge together again to form the interlobular veins, which become the arcuate veins, which become the interlobar veins, which become the renal vein. That's the blood supply to and from the kidney. So shifting gears, looking at this again, because I know that's a lot of information. Renal artery becomes a segmental artery. Segmental artery goes in between the lobules, becoming the interlobar artery. It arcs over the top of the pyramids, becoming the arcuate artery. The arcuate artery extends into the cortex, becoming the interlobular artery, which is going to branch off into the afferent arterioles. The afferent arterioles go into the glomerulus and become the efferent arterioles. The efferent arterioles come out and become the peritubular capillaries and the vasorecta. The vasorecta and peritubular capillaries are going to drain into the interlobular vein, which merges into the arcuate vein, which merges into the interlobar vein, which becomes the renal vein. If you notice, the one thing that we don't have here is we don't have a segmental vein. For some reason, we don't have a segmental vein. Don't ask me why, I don't know. They just chose to not call it a segmental vein. So the interlobar vein is going to branch, is going to merge to form the renal veins. Here, Hazers. Hazley, come here. Where, little miss? Oh, well, no, come here. Sorry, guys. My teaching assistant has arrived. Come here. Booyah. So three major functions now that we've talked specifically about the histology and anatomy of the kidney. Three major functions of the kidney: glomerular filtration, tubular reabsorption, and movement and tubular secretion. Mom, now that you're here, would you bring me my Mountain Dew bottle that's sitting there? I'm going to use it as an object lesson. Tubular filtration, so substance, the blood moves into the glomerulus. Thank you. The blood moves into the glomerulus. And as it moves into the glomerulus, filtration is going to occur via those little, all these little filtration slits. And through things will move through this filtration membrane here. And so not a lot of substances, fluid is going to enter this capsular space. As it moves into this capsular space, it's going to drain into the proximal convoluted tubule. In the proximal convoluted tubule, some things are going to get reabsorbed from this filtrate that's running through here. And some things are going to get secreted into it that were not filtered out initially. So three major processes going on in the kidneys: glomerular filtration, tubular reabsorption. Much of what's filtered out is going to get returned to the blood. And tubular secretion, things that were not filtered out are going to get moved from the blood into the filtrate that's within this tubule, this nephron loop. So just to think of this, and this drink, I don't know if I told you before, I need to stop drinking this kind of stuff. And so I'm just going to keep referring to it as being very toxic. I didn't realize until recently that the major ingredient outside of water is high fructose corn syrup. It's terrible for you. And if I'd realized that was the major ingredient, I thought it was sugar. I was fine with sugar. I'm not fine with high fructose corn syrup.
But it's Mountain Dew.
What is your point, Becky?
My point is, it's Mountain Dew. Yeah.
He's like, I'm not even going to tell you what my point is. You should guess.
Yep. Yeah, I'm gonna just mute myself.
And you know what? Pepsi is nasty. Coke is nasty.
I love Pepsi.
So, what, Casey?
I love Pepsi. Sorry.
We
Oh,
all have our vices.
Yes,
No
we all have our vices. So because we know that this is this toxic drink that Becky and Casey both hate. Think of this as this is what my nephron. And within this is a bunch of fluid. This is the filtrate. This has got what got filtered out of the plasma into that glomerulus, into that glomerular capsule floor space, and is moving through the proximal convoluted tubule. When that's occurring, most of it is going to get reabsorbed back into the blood. So most of it's going to leave the bottle here, and a bunch of vessels are circulating around this. Most of it is going to get returned to the blood. However, some things that didn't get filtered out initially are going to get introduced into it as it moves throughout the nephron. So we got three main processes: filtration, reabsorption, and secretion, where more things will be introduced into it. So in the proximal, everything is filtered out. Everything that's going to get filtered occurs in the glomerulus. Things that are going to be reabsorbed or secreted are going to occur throughout the rest of the nephron. If you look here, one other thing to keep in mind, because it's always a great idea, is if you remember, I told you that the blood flow is opposite of the filtrate flow. Looking at the vasa recta, it's going to be opposite of the flow of the filtrate. Keep that in mind. So a summary slide showing this. glomerulus is going to filter small solutes from the blood into the filtrate in the loop in the nephron. Proximal convoluted tubule does most of the reabsorption. It's also going to work to adjust the filtrate's pH. It's going to alter the filtrate pH to alter the pH of the blood. So that one of the major jobs of the kidneys and with the lungs is to work with the pHs and adjust the blood pH. The ascending loop of Henle, or excuse me, descending loop of Henle, is going to allow water to pass from the filtrate into the interstitial fluid or capillary surrounding the descending loop of Henle. The ascending loop of Henle is going to absorb sodium, reabsorb sodium and chloride from the filtrate into the interstitial fluid. Distal convoluted tubule is going to selectively secrete certain things and reabsorb different ions to help maintain the blood pH again and maintain electrolyte balance. The collecting duct is going to reabsorb solutes and water from the filtrate. That's the main, this is just a run through of what we're looking at when we talk about kidney function. We will go through a lot more of this again next week and when we talk about it in lecture. But so the glomerulus does a lot of filtration. It does all the filtration. Proximal convoluted tubule does reabsorption of almost everything. Sodium, glucose, potassium, amino acids, bicarbonate, phosphate, urea, water. It's also going to be involved in secreting hydrogen ions to help maintain the blood pH and secrete foreign substances. The loop of Henle, its major job, its main and only job, is to concentrate the urine. The descending loop is involved in water reabsorption. The ascending loop is involved in sodium reabsorption. The distal tubule is involved in reabsorption of sodium, water, bicarbonate, and secretion of potassium, urea, hydrogen ions, and ammonia base, and some drugs. The collecting duct is involved in reabsorption of water and reabsorption or secretion of sodium, potassium, hydrogen ions, and ammonia. You have questions for me right now? So major substances that are secreted. Proximal convoluted tubule. In the proximal convoluted tubule, you secrete a lot of hydrogen ions. Nothing is secreted in the descending loop. Nothing is secreted in the ascending loop. In the distal convoluted tubule, potassium and hydrogen will be secreted. In the collecting duct, potassium and hydrogen will be secreted. I'm going to try to find something. Bear with me. I only think about this stuff when we start going over it. All right, let's look at this. So the loop of Henle, and we'll see how good it is. The loop of Henle, explaining this, how the loop of Henle is going to concentrate. Louis is going to concentrate the urine. He sounds downright vicious. I know he does. Oh, well, that doesn't work. Oh, here.
Concentrate urine in the kidneys. The loop of Henle. Hiya, welcome to Biomed Sessions with me, Ruse. Today we're going to be discussing the loop of Henle and the way it helps to concentrate urine in the kidneys. The loop of Henle is found between the proximal convoluted tubule and the distal convoluted tubule in the nephron. There are actually two types of nephron in the kidney, cortical and juxtamedullary. This happens to be a juxtamedullary nephron because of its long loop of.
So the cortical, meaning that the loop of Henle stays up in the cortex. Juxtamedullary, meaning it's going to dip down into the medulla.
Henle, and the fact that it dips down into the medulla of the kidney. This type is well suited to the role of helping to concentrate urine. As discussed in my function of the nephron video, filtrate moves through the tubules and eventually exits the collecting duct as urine. But what we want to know is, why does the concentration of filtrate increase as you go further down the loop of Henle? Osmolarity is the concentration of a solution, often expressed as milliosmoles per liter. Filtrate in the proximal convoluted tubule has an osmolarity of 300 milliosmoles.
Think of osmolarity as meaning the concentration of something, whatever it is. It's the concentration.
Osmoles per liter, the same as the surrounding interstitial fluid. This means that the filtrate is isoosmotic with its surroundings, but it's a very different story in the loop of Henle. Let's zoom in. Let me give you a brief recap of what happens here, but if you want more details, including information about permeability, do go back and watch my previous video. Okay, so in the thick ascending limb, sodium ions are pumped out, and negative ions such as chloride follow, making the medulla a quite.
If you remember, remember the blood is flowing opposite. So filtrate is moving this way. The blood is flowing this way. When sodium is pumped out, where is it going to go? It's going to go into the blood. And so the result is that as the sodium, as the blood moves this way, it gets very concentrated with sodium. Well, how does water move? Water moves from where where there's the lowest concentration of something to where it's a higher concentration. So water is going to move in the opposite direction. So water, as you pump sodium into the blood here, the water, hey, Louie, the water is going to move into the blood here because it's more concentrated. The blood is more concentrated than the filtrate is.
A concentrated and salty region. Water leaves passively from the fin descending limb because of the surrounding salty environment. And as the water leaves, the filtrate in the descending limb becomes significantly more concentrated. In addition, the salty medulla is also a major reason why water is able to move passively out of the collecting duct and be reabsorbed back into the blood, thus leaving behind more concentrated urine. But let's pretend that the filtrate is entering the loop of Henle for the very first time. Naturally, because the filtrate is coming from the proximal.
Guys, I'm going to end this. I'm going to do one other thing. I want to look for one other thing. Bear with me here.
Convoluted tubule,
Nope, stop.
it will have this.
We're going to look for a functional nephron instead.
Say it's alright. Hiya, welcome to Biomed Sessions with me, Ruth. Today we're going to be discussing the function of the nephron. Here we have our nephron, the unit of the kidney responsible mainly for the production of urine in order to get rid of excess water and toxic waste products. There are approximately 1 million nephrons in each kidney. At this end of the nephron, blood enters in via the afferent arteriole, passes through a network of capillaries called the glomerulus, and leaves via the efferent arteriole. As this occurs, components of the blood are filtered out into an area known as the Bowman's capsule. The filtered components, collectively known as glomerular filtrate, pass on into the tubules. Eventually, filtrate enters the last part, the collecting duct, and exits as urine. In men, the kidneys typically produce about 180 litres per day of this filtrate, yet only 1 to 2 litres of urine are produced each day. This means that only 1% of the filtrate manages to leave the nephrons. So what happens to the other 99%? For the most part, filtrate is reabsorbed back into the blood at several locations along the tubule. But how can reabsorption occur? Well, the efferent arteriole doesn't just end there. It branches out to form capillaries which surround the tubules of the nephron. Reabsorption is the movement of substances out of the tubules across the surrounding interstitial fluid into the blood of the capillaries. Now, whilst we're on the topic, we might as well discuss secretion, which occurs in small amounts in the nephron. This is the process whereby substances move from the blood through the interstitial fluid into the tubule. To make things simpler, let's remove the surrounding capillaries and zoom in on the first part of the journey where filtration occurs. I've covered this process in detail in a previous video, which I've linked for you to check out. But basically, most components of the blood, except for blood cells and the majority of proteins, are squeezed out between the pores of the glomerulus to reach the Bowman's capsule. So the glomerular filtrate contains substances such as water, glucose, amino acids, and inorganic ions such as sodium, chloride, potassium, and bicarbonate. It also contains the waste products, creatinine and urea. Small amounts of these substances in the blood are okay, but they are harmful in large doses. Hence, the body rids itself of significant amounts via the kidneys. The next destination for the filtrate is the proximal convoluted tubule. Convoluted simply means twisted or coiled. This region is lined with simple cuboidal epithelium, and substances pass from the basolateral surface to the.
You remember, simple cuboidal epithelium is best used for reabsorption. another thing that we see on these is that there's a lot of microvilli. Because that's what microvilli, that's the reason we have them, is to increase the surface area to allow for better reabsorption. So in this area of the proximal convoluted tubule, you have a lot of simple cuboidal epithelium with a lot of microvilli, increasing the surface area to allow for better absorption in the proximal convoluted tubule.
Apical surface of the cells and out into the interstitial fluid. Approximately 65% of sodium ions are reabsorbed here through various methods. Positive attracts negative, so naturally wherever sodium ions go, chloride ions follow. Other negative ions do so too. As you may know, NaCl is the formula for common table salt, so it would be pretty salty outside the tubule if it wasn't for the fact that 65% of water leaves by osmosis. In addition, 65% of potassium is reabsorbed, as well as 90% of bicarbonate ions, which are important in maintaining the pH of the blood. But glucose...
You guys, what's bicarbonate? What's bicarbonate? Bicarbonate is a great base. And so when you're increasing the amount of base within the blood, the result is that the blood is going to become more basic, right?
And amino acids are the champions here, as around 100% are reabsorbed back into the blood to be used in processes such as respiration and making proteins. Note, not all urea leaves the nephron in the urine, as about 50% is reabsorbed. And secretion? Well, ammonia as well as various medications are secreted into the tubule. The next part of the nephron is the loop of Henle, which has a descending limb in which the filtrate travels down, and an ascending limb in which the filtrate travels up. The thin segments of the loop are lined with squamous epithelium. Now the loop of Henle...
Why do you think you'd have simple squamous there, not simple cuboidal? What do you use simple squamous epithelium for? What do you use it for?
Is it used for like absorption?
You're close. What about diffusion? It's not so much absorption as it is diffusion. Just
Okay.
things are going to move through very easily. So this is where we're gonna get a lot of water diffusion. It's gonna move via osmosis.
Henle dips down into a region of the kidney known as the medulla. This region is highly salty. Why? Because sodium is actively pumped out of the thick ascending limb, followed by...
So it's gonna be actively pumped out here into the blood. The blood is gonna flow around here. You guys, this is probably the most complicated part of the kidney. And I'm learning more and more how to explain it better. But the blood is moving around like this. Sodium is being actively pumped in over here, making the blood very concentrated. And so as the blood moves here, water is going to flow from here, the descending limb, into the very concentrated blood. That's what we call this counter current multiplier. Are you looking for Abby? I'll watch her. She's over here on the chair.
by chloride, but water itself cannot follow because the ascending limb is impermeable to water, hence the interstitial fluid becomes salty. The descending limb, however, is permeable to water, but has very low permeability to ions such as sodium and also urea. So as the filtrate travels down the descending limb, water leaves by osmosis because of the salty environment of the medulla. By the time the filtrate reaches the bottom of the loop, it is highly concentrated as significant amounts of water have left. However, the story is different in the ascending limb, whereby any water that remains cannot escape the filtrate. Sodium chloride, on the other hand, leaves passively from the thin ascending limb, then is actively pumped out of the thick ascending limb. After these processes have occurred, the filtrate is dilute. In total, approximately 25% of sodium chloride is reabsorbed from the loop of Henle. In order to avoid cell damage, the amount of water and salts in the blood needs to be kept regulated, and the nephron plays a vital role in this. The distal convoluted tubule, which is made up mostly of simple cuboidal cells, is the place where initial...
So this is another area where we're going to get a lot of absorption. Not as much as we saw over in the proximal convoluted tubule, but we are going to see it here.
Adjustments are made to the filtrate. Under the influence of the hormone aldosterone, sodium...
Do you remember what aldosterone does from earlier today? I know there was a lot of hormones, so if it's a blur for you, I understand. What did aldosterone do? Aldosterone is going to result in sodium reabsorption from the filtrate into the blood that's surrounding here. Remember, the proximal convoluted tubules are surrounding here. And if it's being actively moved from the filtrate into, into the blood, the result is that water will move also. Because the more, just like we saw over here in the descending loop of Henle, as it gets more concentrated, water will follow. So one thing that we want to keep in mind, especially when we're talking about the kidneys all the time, and this is the best and easiest relationship in the kidneys, water follows sodium. Write this one down. Water follows sodium. Many times your body will regulate its water volume by how it regulates sodium. If it increases sodium with many times with the intent that water will get pulled in with sodium.
Is reabsorbed, followed closely by chloride, whilst potassium or hydrogen ions are secreted into the tubule. Almost all remaining bicarbonate is reabsorbed, and although the distal tubule is normally impermeable to water, small amounts may be reabsorbed here too. The collecting duct, which is composed of principal and intercalated cells, is where the final adjustments take place before the filtrate leaves as urine. Here, sodium chloride is reabsorbed in addition to urea, although sometimes urea can re-enter the tubule at the loop of Henle in a process known as urea recycling. But what about water? Levels of water in the collecting duct are regulated by the hormone ADH, which acts to retain water in the body by enabling it to be reabsorbed back into the blood. For example, if you are dehydrated, ADH allows aquaporins, aka water channels, to be inserted into the epithelium, allowing water to be reabsorbed back into the blood. Remember, the medulla is salty, so if water is given the opportunity to leave, it will. On the other hand, if you're overhydrated, a lack of ADH will mean that the collecting duct is more or less impermeable to water, so excess water can pass out into the urine. In general, urine contains water, urea, sodium, chloride, potassium, and creatinine, as well as other inorganic substances. Okay, hopefully you found this tutorial.
I wish I'd discovered that video earlier. I won't say anything though, as I just
Real helpful.
went through this in another class. Wish I'd seen it earlier. Okay.
I feel like it did a good job, just so you know.
It did, and it's short. It's
Yeah,
good and
it was,
Go
it was
ahead.
good.
No, I was gonna say, are you gonna post those videos?
Yes, yes,
My
Yeah,
ADHD wasn't-
I appreciated that. Thank you.
you're welcome. She did do it. She did a great job. Yeah, I'll post it right after class. All right, so let's see here. So continuing on, looking just a little bit more, like I said, this is not a very long lab. Actually, you guys, let's take 5 minutes. Let's take 5 minutes, come back at 1:41, okay?
All right, good. I have to let my dogs out. Thank you.
Come here, missus. Oh, what do you do? Oh, tired. Oh. All these cups are recyclable. All right. Well, you're right for now. Right. All right, you come here. Oh, Hazel, come here. Come here. Come here. Come here. Hazers. Hazel. Come here. Oh, come here. I'm not trying to hurt you, little girl. Okay. All right, so one of the last parts about talking about the kidneys here. Looking at the rest of the kidney, the ureter made of transitional epithelium. If you remember, that's the kind that stretches and ruffles when it's relaxed. The inside, the lumen, the transitional epithelium, lamina propria underneath the deep to the transitional epithelium, mucosa, muscularis, and adventitia. Muscularis meaning a lot of smooth muscle. We're going to see these same layers again. Epithelium, lamina propria, mucosa, muscularis, and adventitia. Now that I can't see any faces, hope you're still with me here. Looking at the male urogenital tract, bladder, urethra, ureter. The urethra starts in the testes scrotum, and it actually wraps around the bladder, moving through the prostate, the internal urethral orifice, prostatic urethra, moving through the prostate, membranous urethra moving through the urogenital diaphragm here, and the spongy urethra moving out through the penis, with the external urethral orifice down towards the bottom. Questions? The female a little different. the uterus laying on top of the bladder almost. When women who are pregnant talk about the baby stomping on their bladder, they're not kidding. So the uterus, the bladder, the urethra. Why are women more prone to UTIs than men are?
Yeah, that's shorter.
It's shorter and it's also more open. If you look at this, this is a fairly closed off circuit. In women, it's not so closed off. The urinary bladder, the internal urethral orifice right where it was in the male bladder. The urogenital diaphragm. So in women, this would be where the membranous urethra would be if we called it the membranous urethra, which we don't call it that. And the external urethral orifice. Looking specifically at the bladder, remember, one thing to keep in mind is that the same layers that we see up here, the transitional epithelium, the lumen, the mucosa, the muscularis, and adventitia, are the same layers that we're going to see in the bladder. Transitional epithelium, mucosa, muscularis, adventitia on the outer layer. The ureters are coming in and entering the bladder through the bottom. This little triangular area in between the two openings, the trigone. A muscle that works to compress the bladder, the detrusor muscle of the urinary bladder. The internal urethral sphincter, right around where the internal urethral orifice is. The external urethral orifice. External urethral sphincter, the urogenital diaphragm right here. Any questions? I'm going to shift gears just for a minute here, talk about two other major things. If you remember this from before, this is what we talked about last week. We'll talk about it again in a week. Carbon dioxide and pH. If you remember, I made the note and I showed you that experiment where you blow carbon dioxide into water and you change the pH. And you make it more acidic because carbon dioxide is a weak acid. And if I increase the amount of carbon dioxide here, I increase the amount of free hydrogen ions. And pH is a measure of the amount of free hydrogen ions. You guys, this is a very important equation. If I increase the amount of bicarbonate here, I'm going to increase the amount of carbonic acid here, and I'm going to increase the amount of CO2 and water here. If this reaction shifts to the left, solution becomes less acidic, more basic. If it shifts to the right, it becomes more acidic because as it shifts to the right, I increase the amount of free hydrogen ions. And since that's the way I measure pH, the more free hydrogen ions I have, the more acidic the solution becomes. So carbon dioxide plus water is going to make carbonic acid. Carbonic acid is going to automatically break down into hydrogen ions and bicarbonate. Memorize this equation. So using that equation,
You go back one. I want to screenshot it. Sorry.
nope, that's all right. I understand.
Thank you.
I used my phone. I took a snapshot of it on my phone. I do that a lot. If you
It's
see
a
me go
good-
like that,
we're-
that's me taking a picture.
We're going to see it over and over again.
Yeah, but at least I have it visually to go back and then I can go back and write it down.
Right. We're going to see it over and over again through the next 3 chapters. Because it's the way your body maintains its pH. It's the way that your kidneys and your urinary system are both working together to maintain your pH. So acid-base balance, this balance between the input and output of hydrogen ions. It's maintained by your lungs and your kidneys. Carbon dioxide is this weak acid, combines with water, forms carbonic acid. That's your weak acid. The lungs prevent this increase in the pressure of carbon dioxide by exhaling it. Bicarbonate is a weak base. Your kidneys work really well to reabsorb or secrete, reabsorb bicarbonate or secreting hydrogen ions to maintain your blood pH. So lungs work on this part of the diagram. Kidneys work on this part of the diagram. My mother will tell you that this is probably one of the most important parts of understanding physiology is acid-base balance. So I'm gonna sift down just a little bit. Arterial pH. When it becomes acidotic, if the partial pressure of carbon dioxide goes up, this becomes respiratory acidosis. If the amount of bicarbonate goes down, meaning you've lost a lot of base, metabolic acidosis, I mean, very acidic. Respiratory alkalosis is when the partial pressure of carbon dioxide goes down significantly. Metabolic alkalosis is when the amount of bicarbonate is going up significantly. The amount of base is going up. So kidneys work by either excreting hydrogen ions or reabsorbing bicarbonates. So there's a complicated diagram that we'll talk about more when we talk about the kidneys. But right now, understand that it's talking about either secreting hydrogen ions. This is the lumen. This is the lumen of the nephron. This is the proximal convoluted tubule. So we can either excrete hydrogen ions or we can reabsorb bicarbonate. Almost if you excrete a hydrogen ion, it's the same thing as reabsorbing a bicarbonate. So looking at the same reaction up here, I'm going to spend, I like spending time with this, especially in the lab where we're not behind, because it will make things easier in lecture. So looking at this equation right here, this is the same thing that we're seeing down here. Bicarbonate and hydrogen ions coming together to form bicarbonate, carbonic acid. Carbonic acid breaks down into water and carbon dioxide. Carbon dioxide diffuses over into the proximal tubule cells, combines with water to form carbonic acid. Carbonic acid breaks down, the bicarbonate is reabsorbed, and the hydrogen ions are secreted. So it's the same as this reaction. Like I said, memorize this reaction because we're going to see it over and over again. Last part, last slide, water homeostasis. Osmoregulation, remember we talked about osmoreceptors in the endocrine system? Osmoregulation meaning regulation of water. Water increases the volume of the blood, which increases the blood pressure. If we increase the blood pressure, we can increase the heart rate. Excuse me, actually, let me say that's different. I'm sorry, that didn't sound right. Water increases the volume of the blood, which affects the blood pressure, which allows the heart rate to lower. Kidneys are their major job outside of helping regulate the pH is regulating water intake and regulating water loss. So when blood water levels rise, the kidneys will add more water to the urine. They do this by just not reabsorbing any water from the filtrate that's running through the nephron loop. The result is that you get a greater volume of urine being produced. The body water levels fall and the result is that the kidneys will add less water to the urine causing body water levels to rise. The result is that you produce smaller amounts of urine and you feel thirsty. You want to drink more water. I think next week, to save us some time in lecture, this is the last slide. And to save us some time in lecture, I'm going to spend some time talking about urinary system physiology during lab, and I'm not going to recover it in lecture. And because but I do want to, right now I want to jump into this kidney dissection and spend some time looking at these kidneys. Are there any questions though?
I'm good.
Okay, I will make sure that I post that video as soon as class is over today. Tarek, are you here? You still here?
Yes.
Okay, I apologize for the last like 2 weeks ago. I should have just told you that I was getting tired when I was dissecting those lungs and needed to be done.
Oh, you're fine. I enjoyed it.
Well, I was short with you and it wasn't really necessary. So
No, you're fine. I didn't think anything of it. Don't worry about it.
Good. Okay, so you guys let me get this out. Bear with me just for a second as I get myself reorganized here.
My sister-in-law's here and she's gonna eavesdrop in on the
That's
dissection.
fine.
But all right.
It's awesome.
All right. Just wanted to give you a heads up so you're not like, wait, we have an extra head.
Oh, no, that's awesome. No, that's
Yeah.
awesome.
She likes it as much as I do. So yep, she's here.
That's awesome. All right,
All right.
give me a second to reorganize myself. Louis, 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 Louis. You're a silly dog. Yeah, but you're doing your job, huh? Yeah, you're a good boy. No, don't bark again. Stop it. Since I have to make sure that whoever it was is gone. Oh, wait, where are? Paisley, stop it. I need some more space. It says okay, you can have it.
Whenever you get a second, Casey needs help logging in on,
Oh, you
she's
know what? I
not
see
there.
her. I see her.
Yeah, thank you.
you. Okay.
Thank
So
you.
I think I want to first, because the kidney that is preserved, it can be preserved for a long time. The fresh kidney that I thawed out has to go in the trash after today. So I'm gonna wait on the let's do the fresh one first. Bear with me just for a second, just getting things set up. Oh, that's not right. Okay, there. Paisley, damn it. So this is the fresh one. And actually, let me show you just for curiosity's sake. This is what it looks like. Oh, you're not even seeing this yet.
I was just gonna say, we can't see it.
Let's see here. Bear with me. Oh, that's not it. Oh, sorry. There. All right.
That works.
So this is the one that's unfixed. Or no, see, this is the one that's fixed. I'm not going to take it out of the bag unless I plan on dissecting it because it stinks really badly once it's out of the bag. But this is the one that's fixed. This one, like I told you, when they're fixed, it doesn't do it justice. This is the one that's unfixed. You notice what I'm saying by the fact that they're very different?
Yeah.
There, nothing about this is, I think it's, you know, until I started teaching Bio 122 here online with Hack, I didn't ever think about trying to dissect organs that weren't fixed. And now I'm realizing all that I was missing out on. A sec. Should have gotten out all my tools first. Bear with me just for a second here. I should have gotten out all my tools and not just my scalpel blade before I got my hands all slimy. Louis, stop it, buddy. Really? Sounds just downright ferocious and nasty, and he's not. He just lets the world know that there's possibly a threat somewhere in the world. I didn't realize just how little this older Belgian Malinois didn't bark until we got this puppy. And now I'm realizing what we're getting into. What I missed out on. But he sure is cute at the same time. Okay, so looking at it, we're looking at the the capsule here. And I think when the butcher takes them out, having never been there when they butchered an animal, because I can handle things when they're before the animal dies. Or actually, I can handle it after they die. I don't want to be there when they butcher an animal, because I just don't handle that kind of stuff very well. But I'm guessing the one thing that they do is they cut into them, because both of the kidneys that I got are cut into. And I think to help get some of the blood out. But this right here, this is the hilum. So this is the entrance of where the renal artery, renal vein, and ureter are like sitting. I'm trying to see if I can tell which of these is the renal artery, which one is the renal vein. I can see a little bit of an entrance right there. Maybe not. Never mind, that's not really an entrance. All right, let's flip it around. If I look right there, that looks like a vessel right here. So I'm going to try. I'm trying to remove. I'm not actually going to try just to remove some of this. One thing that when you do dissections, the most important thing to learn is that your finger is your best dissection tool. Rather than just start cutting away at things, if you use your fingers, you're less likely to cut through something that you're going to try to find later. But I'm wondering, maybe not. Okay. There's a hole right there. Nope, that's not a hole, Mary. All right, what I'm going to do is I'm going to make a cut, and I'm going to cut right through here. And bear with me, guys. I've never dissected an unfixed kidney. I've done a lot of fixed kidneys, but not unfixed kidneys. So we're gonna see how well this works out.
What is the actual difference between a fixed and an unfixed? I might have missed that.
The major difference is that they use formaldehyde.
Okay.
And what it does is it essentially makes all these covalent bonds between all of the structures.
Okay.
And so it just tightens it all up. And that's,
Interesting.
I mean, have you ever felt a dead body like at a funeral home?
At recently dead body when I had to do post-mortem care at the hospital, but yeah, no.
When if you've ever felt a dead body like in a coffin, I'm not telling you to go to a funeral home just to try it out.
Yeah, I'll pass on that.
Are you sure? Come on, Becky. But if you when they feel really hard and really stiff
Okay.
or waxy.
Okay. That's good. I was like, fixed, not fixed. I figured I'd finally ask.
Good question. Okay, I'm trying to be fairly careful here, partly because I don't want to cut my finger. I have not had a tetanus booster in a long time. And this would be a really good way to nail myself good. But I'm just trying to separate it a little bit. Oh yeah, okay, now I'm starting to see stuff here. Maybe. Oh yeah, okay. Would you guys, because I'm trying to think, we have a liver, but there's not a whole lot to the liver. When I get to that point in class, I'll show you this liver, but there's not a whole lot to it. But I'm getting some eyeballs for my biology 121 class, and I know that Dr. Weeks, not to keep going.
No comment.
No comment. I agree with you. But did he ever do any?
Oh,
Casey and I can vouch for that. It was absolutely nothing. It was PowerPoint and going over questions, and that was it. And him doing flick of the lighter, and yeah, it was,
cigarettes.
Did he do any dissection with you at all?
He did. No, he did. And I'm not
No.
discounting. My opinion is he did nothing more than the basic, which
Okay.
is, yeah, like you know, Casey and I talked to you that one day about everything, but no, he did not go above and beyond. He did nothing of this sort.
Well, he no longer works for Hack.
Oh, thank goodness.
I was like, oh, so my review worked.
Well, another student, and so I'm going to keep anonymous here, but another student and I that is in this class, we talked about it for a while one weekend, and we tried to look him up on the school site, and he's no longer here.
Wonder why.
I mean, and I think for future students, it's a good thing because my grade in that class, my grade overall, like with you, was one thing, and then having stuff with him reflected an overall thing, and it was disappointing because now I see the difference in my grade.
Yeah.
But very frustrating.
I
Agree.
For anybody who had Joel Bacon, did he do any dissections with you of the eyeball?
No, in fact, you're talking about the special senses.
Yeah.
No, because he chose to skip that and do the nose or something.
Oh, really?
Yeah.
So it's a long story, but if you had me for 121, you know that I focus on hearing with the special senses, because that's what I most understand, hearing and balance. But there, in my 121 class that I'm teaching this semester, one of my students has a little girl who is really into anatomy also. And she's like 8 years old. And she told me, with her dad's permission, she told me that her favorite thing to look at was the eyeball. And
Oh,
so,
that's crazy.
yeah. And so I've ordered some eyeballs on just really just for her.
What class is that? Can I sign in and watch it?
Yeah, I'll say.
Yeah, that's gonna be interesting.
Well, no,
Yes.
I was gonna, no, well, let me explain what I was gonna say. I'm sorry, now I'm getting distracted. I'm tired. Do you want me to dissect an eyeball for you?
I'm in
I would
for
like
it.
Okay.
Yes.
You're like, what? We'll do it.
I
So-
would love to see it.
All right, let me see what timing wise, what we've got towards the end of the semester. And I would, yeah, you could also come into that class. I mean, the nice thing about these online classes, it doesn't matter how many students there are. So I'm slowly cutting into it. If you look here, you see, here's the renal cortex. Here's the pyramids. Here, right here. Everything, I'm gonna sit down. Right here, as we keep going in, we'd find a minor calyx.
Not at
gonna-
all what I would have expected.
Yeah, it's not, is it? I'll tell
No,
you,
not at all.
when it's fixed, it's very different. It's not the same. I'm just trying to gently cut them apart. So right here, here's your minor calyce. Here's your minor calyce. Here's the major calyx. Minor calyx. Major calyx. Mom, can you come and help me really quick? I'm gonna have my mom help me orient my camera a little better because my hands are all slimy.
Way to go,
Number
mom.
two.
I love mom.
I know.
Let's see. From this angle.
Yeah, just if you can even, shift the books forward. Hopefully not knock my camera into my bloody gut.
How's that?
It's the wrong way, I think.
Okay, we still get clear.
Here, Kat.
Yeah, down a little further, like that. Yeah,
That's better.
So now
I
can
think that will work.
that look good?
Yeah, that's better.
Good enough?
Thanks, Mom.
Sure.
Okay. So, yeah, looking at it, here's the cortex. I'm guessing, looking at this, like I said, I've never dissected an unfixed kidney. But looking at this, if you see, there's a color pattern difference right here versus right here. And then the pyramids are right here. I'm guessing that this is the capsule. This is the cortex. You don't see that on fixed kidneys. I'm pretty sure you don't. So this is the capsule. This is the cortex. This is the pyramids. And if you look, you can see that the cortex is going to descend down in between the pyramids.
Is this from a pig?
Yeah.
Okay, it makes sense why it's so much more bigger than the sheep one.
Well, I actually, the one that I have behind me is also from, I think it's also from pig.
Gotcha.
So looking here, and I don't know if this is a cut that I made, which is possible. But that looks like the internal part of a calyx. Actually, let's see here. Put this down. Oh. One thing that there's almost like a connective tissue skeleton where there's a lot of firm tissue that you have to cut through. So yeah, if you look here, you can see, I think this is the capsule. Capsule out here, cortex, the pyramids, the renal papilla, moving into a minor calyx that would move into a major calyx down here. Let's see here. So you can see the striations. So here we're, just a sec. Okay. All right, that's blood's going away. Hi, Bobby. So right here, there's your minor calyx, there's your major calyx. This whole area right here, this would be the sinus. I honestly, now that I'm doing this for the first time, I think the undissected kidney gives you a lot more than the fixed one does.
My sister-in-law and I were both like, that's just not what I expected. It's just so different.
Yeah,
Yeah, me either, not at all.
I mean, it's fascinating
Yeah.
either way, but yeah, it's not in my, like what I thought and what I'm seeing are two totally different things.
yeah. I'm going to, let's see here. Yeah. So minor calyx, major calyx. This whole area right in here, the renal sinus. Lots of connective tissue. And if you remember, there was that part that was hanging out the back. I just pulled it out through the inside. I'm going to try something else because I've just never seen. I'm going to cut through one of the pyramids right here and see just what kind of shape they are. Just 3D wise, what do they look like? If I can see, we'll find out. No, not really. Not really. So that's looking at it from a side view. You can still see part of the pyramid right there. Anything that you want to see that I might be able to find? Right here, I think that's an opening to a calyx. There's a pyramid opening into a minor calyx. Like I said, outside of my my X-Acto blade that I got at Walmart, my tweezers that I got at Walmart. I think I actually bought them at a dollar store, maybe. The pan is a kitty litter box. And I bought the blue mat online, a dissecting pan. And the pins. The rest of this came from stores here in town. But minor calyces, major calyces. I'm trying to see if I can actually open into a minor calyx, and I don't know if I can. It seems like it's pretty attached on there. Yeah, it's pretty attached on there. Maybe. Yeah, maybe. So I think putting my probe in there, I think I did. I think I'm in a minor calyx there. Because I can feel, you can kind of see it right there, slipping into that. Yeah, I can't really see, I wish I could see the renal artery, and I can't really see it on here. Is there anything in particular you want me to try to find? Any questions you want to ask me? Okay. Guys, if you want to leave, feel free to leave. If you have questions for me, let me know. And have a wonderful week.
Thanks, you too.
You're welcome. Oh, Terry, did you see? Yeah, I think he's already gone. Never mind.
Do you want me to wait
Yep.
so we can
Hey,
talk?
Casey, yeah, wait just a second longer.
Okay.
Okay. Let me clean myself up just a second.
Take your time.
Okay. Let's see here. Okay, just a sec, Casey, one more thing. Quit. Oh, no. Okay. Toy and Jade or Zena, are you here? Joan Arlene, are you here?
Yes,
Yes.
Okay. Casey, do you want to talk? You sent me that email and I don't feel like I was really great about responding. What can we do to get you caught up?